तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So far, we have been discussing various methods to assess the dynamic behavior of linear time invariant systems. The methods that we have discussed broadly fall into two classes. One, the methods of differential and equations or difference equations as may be appropriate. The second one is the operational methods or the transform methods, which are the Laplace transform method and the Z transform method that we have discussed. Now, let us pause for a while and see what are the relative merits of these two classes of solution for the dynamic performance of a system. The differential equation and the difference equation approach is more fundamental, because the characteristics of the elements which constitute the networks or systems are given fundamentally in terms of differential or difference equations, and therefore, this is a more fundamental approach. And further, these methods can be extended to the case of nonlinear and time varying systems. On the other hand, the difficulty with this differential and difference equation approach is that you have to contend with calculus or an equivalent operation in the case of difference equations, and for a complicated differential equation, say of an nth order, you need to have n initial conditions which may not always be available from the physics of the problem. So, the initial condition and the initial values of the various derivatives have to be specially found out, and this poses some problems. Now, look at the transform methods. In the transform methods, the calculus part is converted into algebra. Similarly, the operation of difference equations is converted once again in a purely algebraic process, and therefore, it appears to be quite convenient. And further, all we need to know is initial conditions associated with the dynamic elements. You do not have to find out the initial values of the higher derivatives, which was the problem in the differential equation approach. But then the problem with operational methods, Laplace transform and Z transform methods, is they are not quite suitable for computer implementation, because after all, computers can handle numerical analysis quite efficiently, and when we talk about Laplace transforms and Z transform methods, the transform methods, you are dealing with functions of S or Z as the case may be, and it is not inconvenient to have computer implementation of handling this, while it is feasible, but it is not easy or convenient to do so. And furthermore, when you want to find out the inverse Laplace transform of a complicated rational function with say a high order denominator polynomial, to perform the partial fraction expansion you have to factorize the denominator, and anyway you have to go to numerical methods, and therefore there again you have problems. Now, what we are going to talk about from this point onwards is the state variable method of analysis, which is an alternative to the two methods that we have talked about so far. The state variable methods is also a fundamental method in that it relies largely on differential equations or difference equations as the case may be, but these differential equations and difference equations are first order differential equations or first order difference equations. Therefore, since we are dealing with first order differential equation or difference equations in the state variable methods, we need to know the initial values of the appropriate variables at one point of time. We do not have to find out the initial values of the various derivatives. Similarly, we need to have the initial value of a discrete time function at one particular point, not at several points for negative values of m. Furthermore, this is convenient for computer implementation, unlike the Laplace transform methods. Therefore, in a sense, the state variable methods have provide you certain advantages which are not present either in the classical differential equation approach or the Laplace transform approach, and therefore, these are quite widely implemented for the computer implementation of the dynamic analysis of systems and networks. So, with this introduction, let us see what the state variable method implies. We broadly define the state of a system as the information about a system at a point of time that needs to be known for the solution or finding out the output under the influence of an excitation specified from that point of time. This sentence may not mean immediately something for you. To put in other words, suppose we want to find out the transient analysis, do the transient analysis of, let us say, an RC circuit under the influence of a certain input quantity. Before you do that, you must know the initial charge in the capacitor. Unless you know the charge in the capacitor on the application of the input, the solution will not be unique. So, this is something which you need to know to find out the output under the influence of a given input. So, that is what is meant by a state, the information that is necessary for a dynamic system, so that from that point onwards we can find out the output corresponding to a given input. It also turns out that the state has another important connotation. Once you know the state of a system at any given point of time and also know the input quantities at that point of time, the output quantities can be deduced algebraically without having to go through any calculus operation. So, these are the two aspects of the state which I would like to illustrate first by means of an example and then define these concepts more formally. Suppose we have a network like this with one inductor and one capacitor and two resistances R1 and R2. Let us say we are interested in these two values VR1 and IR2. These are the two output quantities which we are interested. This is the input excitation. So, in order to solve this particular circuit, given the value of E from say t equals 0 onwards, the solution can be unique only if you know the initial value of the inductor current and the capacitor voltage. So, IL and VC, their values at time t equals 0 on the application of the input must be known. So, the two variables that we are talking about, IL and VC, constitute what is this called state variables of this particular circuit. This is one choice of the state variable. So, IL and VC, these two together constitute the state of the system. So, we need to know the values of these two variables at a particular point of time, so that we can predict the behavior of the circuit and in particular calculate the various output quantities under the influence of an excitation uniquely. Unless this is specified, the solution of the problem is not unique. That is one aspect. Secondly, suppose you know IL and VC at any particular point of time, you can calculate VR1 and IR2 purely algebraic way without having any calculus, because you can say if you know the value of IL here, I can replace this by a current source of value IL, and then the capacitor voltage is VC, therefore, I can have a voltage VC here, and this is E. So, if all these values are known at a particular point of time t1, we see t1, E t1, then Vr1 at t1 and Ir2 at that point. So, if you know the state at particular point t1 and you know the excitation function also at t1, these values can be calculated purely as in a non-dynamic system, purely as a resistive system, because we now have a purely resistive network under the influence of several sources, and the solution is one that pertains to an instantaneous system or a non-dynamic system at that particular point of time t1. And this replacement of inductor by a current source and the capacitor by a voltage source, as you know, are permitted by the substitution theorem. After all, whether you have an inductor carrying a current IL or a current source having strength IL, the circuit behavior is the same. So, as far as the state is concerned, then we have two particular points of significance. One is, that is the information we need to know about a system so that we can predict the future behavior under the influence of a specified excitation function from that point onwards. Secondly, once you know the state of the system, that means the values of these, the outputs at that particular point of time can be computed purely through an algebraic process involving the values of the state at that particular point and the excitation function at that time. Now, you see the contrast between a dynamic system and a non-dynamic system. A non-dynamic system is a purely resistive type of system where you have either resistances or dependent voltage sources, dependent sources, and so on and so forth, and there if you are given excitation functions at a particular point of time, the various outputs can be calculated purely through an algebraic process. So, in the state variable technique, what we try to do is, we try to find, first of all, find the state of a system as a function of time through a calculus part, then use that information to calculate the outputs purely through an algebraic process. That means you separate the problem into two halves, one involving calculus, the second part involving purely algebra. Now, as I mentioned, the information regarding the state is necessary because to solve a problem, because that is a sums up in a dynamic situation the entire past. Whatever information that we need to know about the past is summarized in the value of the state at that particular point of time t. Let us say t equals 0. We would like to find out the transient solution from t equals 0 onwards. All we need to know about the past is the value of the state at t equals 0. We do not have to worry about anything else regarding the past. So, in a sense, it summarizes the essential information about the past that is pertinent to the future behavior of the system. In a sense, therefore, it is a link between the past and the future, and the essential link that is necessary for the solution of the transient problem. And secondly, once you know the state, you can find out the output as a function of the state variables and the excitation functions purely through an algebraic process. That is the essential principle of this. As seen in this example, the state is described by a set of dynamically independent variables IL and Vc in this particular case. In general, we have in a given system or a network, the state is described by n dynamically independent variables, and these are called state variables. The state variables are a set of dynamically independent variables which we use the, let us say, n in number. So, we regard the number of variables as n, and those n variables together constitute the state. So, if the n independent variables are x1, x2 right up to xn, so these are the set of n independent variables which together constitutes a state, and therefore the state is normally represented by means of a column or a vector of state variables. and the entire vector is given the symbol x. So, x is the state vector, x is called the state vector. Simply state or state vector, and the various n components that we have got x1 to xn are called the state variables. In the case of an electrical network, capacitor voltages and inductor currents constitute one particular choice of the state variables. It is by no means unique, you can have several other combinations, but then this is a fundamental way of doing this, and we will say the capacitor voltage and inductor currents constitute the state variables. Normally we take it to be that, but as I said, this is by no means a unique choice, but this is most straightforward and appropriate choice. So, we have, suppose in a general situation we have a dynamic system which has several inputs. Let us say we, in this particular case we have E as the one input, but suppose we have several inputs U1, U2 like that, let us say UK, and we have several outputs, say Y1, Y2 on up to Yn. So, we would assume that in a general situation we have several inputs and several outputs, and the state in this, the state of the system is described by x1, x2 up to xn. This is the state. So, we have three sets of quantities to deal with. These are the inputs and these are the outputs, and this is the state which are internal variables of the dynamic system. So, it turns out that to assess the performance of this dynamic system, we first try to solve for the state vector. We do this by having the solution like this: x1 dot, x2 dot, x3 dot, that means the various derivatives of the state variables. We set up an equation of this type, a matrix A xn plus another matrix B U1 to, I think we put UK, therefore I can write this as UK. So, to set up to solve for the state, we form an equation like this. The derivatives of the various state variables expressed as a vector is obtained as the solution of this equation, where there is a matrix A multiplying the state vector x1 to xn plus a matrix B multiplying the input vector u1 to uk. And once you have solved for this vector, you get the output y1 on up to ym as another matrix C multiplying the state vector xn plus a fourth matrix D multiplying the input vector uk. So, that is how we plan to find out the dynamic performance of the system, a multiple input multiple output system. So, this is the first equation. This is called the state equation and this is called the output equation. The first equation is a matrix equation. We have to solving for x1, x2, xm. So, it is all are differential equations. Each equation represents a differential equation of first order, because x1 dot is expressed as a1 times x1 plus a2 times x2 plus an times xn plus something else. Therefore, this is the first order difference equation in x1 dot. The second row represents a first order difference equation in x2, the third row a first order difference equation x3 and so on, but they are all coupled. So, because x1 dot involves x2, x3, xn also. So, the first set of equation, this whole thing is n first order differential equations, n coupled first order differential equations, because the differential equation in x1 dot involves x2 and xn also. So this is a set of n coupled first order differential equations. First order differential equations. And the second one is a purely algebraic equation. Once you have solved for x1 to xn and you know the input functions u1 to uk, y1 is obtained purely algebraically substituting the values for x1 to x1 you already find out and u1 to uk which you already know. So these are algebraic equations. What I have discussed here is what is applicable to a continuous time system. We will later on, we will talk in the first instance about continuous time systems only to begin with. At the end of this treatment, we will also see how the equations come about for a discrete time system. So from this point onwards, let us assume that you are dealing with a dynamic system, which dynamic continuous time system. Now if the system happens to be linear, and furthermore, I mean this is, we assume the system is linear here in this example already, and furthermore if it is a constant parameter system, so I will say linear dynamic system with constant parameters. So if the system parameters are constant, that is a time invariant system, the entries in A, B, C and D also turn out to be pure constants, pure numbers. They are not functions of any either t or anything. So they are A, B, C, D are matrices of constant numbers. So this whole set, these two equations can be more conveniently be written as x is x dot equals ax plus bu and y equals cx plus bu, where each one of these entries is a matrix. X dot is a column matrix, which is a column matrix is also called a vector also. X dot is a vector, a column matrix. A is a matrix of dimensions n by n. As you can see, A is a matrix because you have got n rows and n columns, therefore this is n by n matrix. As far as B is concerned, it is coupling the input quantities with the state variables, therefore it must have n rows and k columns. In C you have got m rows and n columns. So the size of this matrix is m by n. The size of the D matrix, you have m columns, m rows and k columns. So A, B, C, D are matrices of appropriate dimensions depending on the input output numbers and as well as the state variables. So A, B, C, D here in this matrix representation of these equations are appropriate matrices of appropriate dimensions. X dot is a vector, is a column, x is a vector, u is a vector, y is a vector, x is a vector. So these are all vectors where u represents the column u1, u2 up to uk. So this can be called input vector. U is the input vector and y is y1 to I should have written ym, I am sorry, I should have written as ym because that is what we have written here. So ym to ym, so this is the output vector. So therefore when you are dealing with linear time invariant constant parameter systems, continuous time systems, you have equations of this type. There are two equations, x dot equals ax plus bu, y equals cx plus du. This is called the state equation, this is called the output equation. Even though we are referring to that as equation, is in effect these are n equations here and you have m equations here. These are matrix equations. So, in terms as a matrix equation, this is called the state equation, this is the output equation. So, to summarize the discussion so far, what we said was, when you are dealing with a dynamic system, you need to have some information about the past before you can predict the future under the influence of a given excitation. And the essential information regarding the past is summarized by the state of the system. The state of the system is constituted by n dynamically independent variables in the system. There are several choices of choosing these n dynamic independent variables. For a given system, the number n is fixed, but the choice of the particular variables is available to you. In the case of a electrical network, RLC network, the inductor currents and the capacitor voltages offer themselves as a convenient choice for the state variables, and therefore we expect if there are n inductors and capacitors put together, then we will have n state variables. We also observed that once we know the state variables, the values of the state variables are the value of the state vector, and we know the excitation functions, we can find out the desired output quantities purely through an algebraic process, as you would do in the case of a non-dynamic system. So, we will, once we have this concept, then the solution of the dynamics of a particular state, a particular system, boils down to writing two sets of equations in this manner. We are talking about a general case of a k input m output system, multiple input multiple output system, and the inputs u1 to uk is given the symbol u. This is the input vector u1 to uk. The output vector y is a m vector. We have got m outputs y1 to ym, and the state vector x1 to xm is represented by x. So, we have three vectors u, x and y, and these are related by this equation, where x dot, the derivative of x with reference to time, is ax plus bu. This is a matrix equation. A and B have appropriate dimensions. A is of course a square matrix of order n by n, that is to be kept in mind, and y equals cx plus du, where for a constant parameter system, A, B, C, D are matrices of pure constants. Now, we observe that we need to have calculus. That means you must solve this first order differential equations, coupled first order differential equations, using various methods available for calculus, and once we have that, the second part is purely substitution of that value for this state vector that you have found out in this. So, x is the value of x you have just found out to be substituted here, u is already known. So, as far as the computation is y is concerned, it does not require any special effort on our part. The main effort would be to solve this set of equations for x. So, this is a set of coupled first order differential equations. That is what we have there. One particular point we should like to mention here is that earlier when we are talking about systems, we said x is the input and y is the output, but in the literature it is conventional to take u as the input. When we are talking about state variable theory, it is conventional to take u, use the symbol u for inputs and y for the outputs, and therefore we have deviated from our standard practice of taking x as input and y as output. In the state variable theory, in the literature, you will find normally x being reserved for the state, and therefore we are following that particular notation in dealing with state variable techniques. So, x is not the input quantity, it is the state. The input is given u, and we should not confuse this u with the u that we use when we deal with unit step functions. Here it is differently, simply they are variables u1 to uk, functions of time. Okay. Let us work out an example to illustrate what we have discussed so far. Let us consider this example in which we have a capacitor and inductor. Let us assume that this particular circuit is excited by a voltage source E, and we are interested in finding out I as the output quantity. So, I is the output quantity. That means our output vector y consists of just one variable, that is I. and let us take Vc, the capacitor voltage, and the inductor current IL as state variables. So, Vc, IL are state variables. So, this is x1 and this is x2 could be, and the input is E. So, this is U vector is only one variable, that is E. So, with this identification, let us try to form the equations x dot equals Ax plus Bu and y equals Cx plus Du in the standard format. Now, we have E equals the current, this is Vc, therefore, the current in this branch C dVc dt, that is 1/4 Vc dot. Since this is a capacitor of 1/4 farad and the voltage is Vc, we would like to express everything in terms of Vc and IL and the input and the output quantities. Therefore, I would like to express the current in terms of Vc, therefore, this is 1/4 Vc dot, and that is the current which passes through this. Therefore, the voltage drop across this is 2 times 1/4 Vc dot. So, if you write the Kirchhoff's voltage law around this circuit, we have to E equals this voltage plus this voltage plus this voltage. And what is this voltage? This voltage depends on the current here. This is IL and this is 1/4 Vc dot. Therefore, the current here is 1/4 Vc dot minus IL. Therefore, I can write E is 2 times, this is 2 times the current in that 1/4 Vc dot plus, that is the voltage across this voltage drop across this resistance, plus this voltage which is Vc, plus the voltage drop across the 6 ohm resistor which is 6 times the current through this is 1/4 Vc dot minus IL. Vc dot minus IL, and that if you simplify this, you will get Vc dot equals minus half Vc plus 3 IL plus half E. This is one equation. Similarly, we must also have an equation involving IL dot. The voltage across this inductor is L di dt. So, 1 times IL dot, that is the voltage across the inductor, and that voltage is also equal to this voltage which is 1/4 Vc dot minus IL times 6. Times 6, and Vc dot is known to us already. Therefore, 1/4 of, for Vc dot you substitute minus half Vc plus 3 IL plus half E, that is Vc dot, which we already know, minus IL and the whole thing multiplied by 6. And on simplifying this, you can show that IL dot equals minus 3/4 Vc minus 3/2 IL plus 3/4 E. And therefore, we can now use these two and write Vc dot IL dot equals Vc IL plus another matrix times E, and using this Vc dot is minus half Vc plus 3 IL, therefore, minus half Vc plus 3 IL plus half E, therefore, I get half. Similarly, IL dot equals minus 3/4 Vc minus 3/2 IL plus 3/4 E. So, this is the state equation. In standard form, x dot equals Ax plus Bu. minus half 3, minus 3/4, minus 3/2, etc. Now for the output, your output I, this is the current that is we are interested in. I equals 1/4 Vc dot. After all, it is the same current that goes through. So I can be obtained as 1/4 Vc dot, and we have the equation for Vc dot already. Therefore, I equals 1/4 Vc dot, that means minus 1/8 Vc plus 3/4 times IL plus 1/8 E. To put this in the standard matrix form, I equals minus 1/8 3/4 Vc IL plus 1/8 E. So in this is the output equation. In the standard form. So in this case, the matrix A is a 2/2 matrix. This is the B matrix. This is the A matrix here. This is the B matrix. This is the C matrix, and the D matrix is a pure scalar 1/8, because we have got only a single input and single output. So this example illustrates how the state and output equations are formed, choosing an appropriate set of state variables, and then you got this situation in the final result in this form. Okay. Let us now look at the the merits of the state variable techniques. I mentioned one merit already earlier, but let us summarize the various merits of the state variable techniques. First of all, there is abundant literature in mathematics on the solution of coupled first order differential equations, which we had to deal with in the state variable technique. So we will mention that abundant literature in mathematics. Mathematicians have developed several techniques for solution of coupled first order differential equations. Secondly, first order differential equations are quite convenient for implementation for programming on a computer. So easy programming on computers. Either analog computers or digital computers. Third, leads to generalizations for nonlinear time varying systems. So the approach of state variable techniques, as we will discuss for linear time invariant situations, the methods can be generalized to be made applicable to nonlinear and time varying systems also in more or less a straightforward manner, even though the solution techniques will be certainly more complicated, but the formulation of equations and so on can be made to follow these analogous lines. Therefore, it leads to a convenient generalization as applicable to nonlinear and time varying systems. And finally, the state variable techniques also provides certain insights. Later on we will see, we will talk about zero input response, zero state response, where principle of superposition can be used, where it cannot be used, and things like that. It provides certain insights into the system behavior, like controllability, observability, and several stability, and so on and so forth. So it provides insights into system behavior in a striking way when you take the state variable approach compared to other techniques. So this is another merit of the state variable techniques. And because of that, in more particularly because of easy programming in computers, the state variable technique has gained a lot of popularity in recent times as compared to other methods of solution for the dynamic performance of systems. The next question that we would like to ask ourselves is, what is the inappropriate choice of state variables, and what is the number of state variables that one would have in a particular system or a network? As I mentioned, the state variables should be so chosen that they are dynamically independent of each other, and at the same time, once you know the state variables, the various quantities pertaining to the system can be deduced algebraically from the knowledge of the state variables. As far as the number is concerned, number of state variables, we can let this is the value n. This turns out to be equal to the number of initial conditions that can be arbitrarily prescribed. So when we are talking about a system characterized by differential equations, we have to give some initial conditions, number of independent initial conditions that can be arbitrarily prescribed. That can be arbitrarily prescribed. This also turns out to be the degree of the characteristic equation. Degree of the characteristic equation. This also is equal to the number of natural frequencies. As you know, the roots of the characteristic equation are the natural frequencies. So all these are one and the same. So the state of a system is characterized by n variables, where n is the number, is the degree of the characteristic equation, is the number of natural frequencies, and is also equal to the number of initial conditions that you can arbitrarily prescribe. That means other initial conditions, if there are any, can be derived from these n independent initial conditions. Now, coming to the particular RLC network, the value of n equals, after all, we can associate initial conditions with capacitors and inductors. Suppose you have 4 capacitors and 3 inductors, we can have 4 capacitor voltages and 3 inductor current, therefore the number is 7. Therefore, for RLC networks we can say n happens to be number of reactive elements that is L and C. However, it may turn out that if 3 capacitors form a loop, all the 3 cannot be independently be specified. Therefore, only 2 can be done because the third becomes dependent on the other 2. Therefore, we must reduce this by number of independent loops containing only capacitors and or voltage sources. We will explain that in a moment. And furthermore, it may be that at a node you have 3 inductors, and therefore all the 3 inductors currents cannot be prescribed independently. If 2 are known, the third is fixed. Therefore, we will say by the number of independent, I will say cut sets. I will explain this in a moment. Cut sets constituted by only inductances and current sources. I will remove this R and current sources. current sources may or may not be present. I will explain this by means of an example. Suppose I have a network like this. You have 2 capacitors and 2 inductors, therefore N happens to be 4. There is no problem about this because there is no loop or a closed circuit containing only C's. Independent loops containing only C's and are voltage sources. There is no loop which contains only C's and voltage sources, because this loop has, this circuit has got an inductor, this circuit has got an inductor, therefore there is no such thing. And about the cut set I will explain a moment later, but we take it for granted there is no cut set of inductors in this particular example. Second example. Suppose I have this, call this C1, C2, E, R1, L1, L2, R2, C3, C4, R3. Now, it is a slightly complicated situation. You observe that there is a loop here constituted by C1, C2 and E. So, if I know some voltage across the capacitance, I know the voltage E, therefore this capacitance voltage gets fixed. Therefore, you cannot arbitrarily assign in the initial conditions for both C1 and C2. Only one of them you can assign. Therefore, you have one loop containing only capacitances and voltage sources. Now, secondly, these 2 inductances have the quality that if you remove these 2 inductances from the circuit, then the network falls into 2 pieces. Or in other words, we can say if there is a current I1 here, this current I2 must return here, because after all I1 enters this whole one port network and that current must come back. Therefore, I1 and I2 are equal to each other. In other words, these 2 currents in L1 and L2 are not independent of each other. If I know this current, I know this current. Therefore, you cannot independently prescribe the initial currents of the 2 inductors L1 and L2, both of them. You can prescribe the initial current for only one of them. And that is what is meant by a cut set. A cut set is really a set of elements on removal of which the network falls into 2 pieces. There is no connection between one part and the other. And if I have 3 inductors coming together, this is also a cut set, because on removal of this particular node gets separated from the rest of the network. That is also a cut set. So, in this example now the N, the number of state variables that we should contend with in the solution of this problem, the number of reactive elements 1, 2, 3, 4, 5, 6. 6 is the number of reactive elements, number of inductors and capacitors put together, minus the number of independent loops containing only C's and voltage sources. There is only one such loop, minus 1. The number of independent cut sets constituted by inductance and current sources, there is only one such, minus 1, therefore this happens to be 4. So, even though you have total of 6 reactive elements, the number of state variables turns out to be 4, and this number of state variables is also referred to as order of complexity. So, this is another name for it. The order of complexity of this network is 4, that is equal to the number of state variables that are required for the solution of this problem. So, in this lecture we introduced ourselves to the concept of state of a system. We mentioned that is the minimum information that is needed about the past of the system, so that with this knowledge and the knowledge of the input that is applied from that point onwards, we can deduce the output. Secondly, we also found that if the state of the system is known as a function of time and the inputs also are known as functions of time, whatever output you need to know about the system can be deduced from these 2 sets purely through an algebraic process without having to solve any differential or difference equations. And we found that a way of representing the state, formulating the equations for the solution is to write x dot equals ax plus bu, where x is the state vector, vector n vector with n components, and x dot is the vector of the derivatives of the state variables. So x dot equals ax plus bu, where u is the input vector, and the output can, once you solve the state equation for x, you can get the output y, various outputs, the y output vector y as cx plus du, where c and d are matrices of appropriate dimensions. The basic problem will be the solution of the state equation. Once you have got that, the output can be obtained quite in a straightforward manner. We worked out an example to illustrate how the state equation and output equation can be formed, and then we said the choice of the state variables should be such that they are dynamically independent, and once they are known, various quantities can be deduced algebraically, and the number that is associated with this, that n, turns out to be the number of initial conditions that can be prescribed in a given system independently. This is also the degree of the characteristic equation, which also happens to be the number of natural frequencies. Applied, this criterion applied to a particular case of RLC network turns out to be that this number n equals the number of reactive elements minus the number of loops which are constituted purely by capacitances and voltage sources, or capacitances alone, or minus the number of cut sets constituted by inductors alone or inductors plus current sources. And this example illustrated that particular case where you have total 6 reactive elements, but the number of independent, dynamically independent variables which constitute the state will only be 4. And this particular number is also called the order of complexity of this network. So we have introduced ourselves to the concept of state, forming the state equations, and the number of variables that are required in a given situation. In the next lecture, we will look at a formal method of writing down the state equations and the output equations. What we have shown in the case of example is an ad hoc approach. It is not in any systematic way we have written down the state equations of the particular example. In the next lecture, we will discuss methods of writing the state and output equations in a more formal manner.